Alright, looks like I'm recording with the right microphone. I'm Dr. A.J. Kumar, PhD. Until somebody starts complaining, I'm going back to 1080p at 30 frames per second, and just because I expect things, the processing to occur instantly, and when it's 60 frames per second, or 4K, I can record in 4K. I don't know if I can get up to 60 frames per second, but I can do 4K video. The problem is well, number one, I'm reading a textbook, come on. But also just the processing bottleneck that it introduces, where I upload a video and 2 hours later it's still not visible. On YouTube they can kind of handle it. 4K they can't handle it all. Rumble actually was better at handling the 4K video, surprisingly. Anyway, so first I want to talk about something I talked about in the last video, which is I couldn't figure out this step, and then I was rewatching the video and I figured out what the step was. This step where I put in X. So this step right here is the distributive property. This step, what this is the observation that the i's range, so the i's will range from 1 to n, let's say, so from 1 to 6. Well, the qj's also range from 1 to 6, just in a different order. And the terms where they don't match will be 0. That's what this step is just deleting terms that are zero out of the sum, which there was an example from the last video towards the end where I showed you how that worked. And then this is just a matrix multiplication, this step, which I understand it a little bit more. So I went from a 0% understanding to now I have like a 70% understanding of this step. But 70% is a lot better. Anyway, we're reading 1.6, the glow-in-the-dark guide to algebra. This is other formulas for the determinant. There are formulas analogous to our definition of the determinant that use expansions by minors on other columns of the matrix, and also ones that use expansions on rows. Again, the notation, switch to green because we're doing the glow-in-the-dark guide to algebra. Again, the notation Aij stands for the matrix obtained. Let me make sure I'm recording the right microphone. The notation Aij stands for the matrix obtained by deleting the ith row and jth column of the matrix A. Expansion by minors on the jth column. Determinant of A is minus 1 to the, oh, for fuck's sake, to the 1 plus j. Okay, that makes sense. You could also do j plus 1 or j minus 1. That makes sense. Aij. So what that means is that if j is odd, then correction, if j is even, if you're expanding on an even numbered column, then you put a minus sign, and if it's an odd numbered column, you put a plus sign there. So I did skim this before. Yeah, this diagram down here. That's what that minus 1 to the 1 plus j thing means. On the jth column, a1j, determinant of a1j plus minus 1 to the 2 plus j. Okay, yeah, that makes sense. All the way up to minus 1 to the n plus j, a and j, determinant a and j. Or in summation notation, determinant of A is equal to sum of, from v equals 1 to n. I'm not going to use the Greek letters. Fuck Greek letters. Okay. Sum from nu equals 1 to n of minus 1 to the nu plus j, a nu j, determinant. Okay, yeah, it's the same formula as above. Expansion by minors on the ith row, right. It's exactly the same except we're going along rows rather than columns. Expansion on the second row gives minus 0. Yeah, you cross out this and this to get 1, 2, 2, 0, plus 2 times 1, 2, 1, 2, okay, minus 1 times, yeah, that would equal 1. Okay, that's, to verify, you can check the properties. I'm not going to do that. You know what I've noticed with Arden is he states the facts very clearly, but his proofs are just unwieldy. The alternating signs that appear in the formulas can be read off of this figure. Right, that makes sense. The notation minus 1 to the I plus j may seem pedantic and harder to remember. It's more useful because it can be manipulated by the rules of algebra. Right. We describe one more expression for the determinant, the complete expansion. The complete expansion is obtained by using linearity to expand on all the rows, first on row 1, then on row 2, then so on. For our 2x2 matrix, this expansion is made as follows. Determinant of A, B, C, D is equal to A times the determinant. Huh. Yeah, that's the same as the minors, isn't it? Yeah, it'll give you exactly the same thing. That's interesting. Yeah. That is interesting. Oh. Yeah, so just stare at this formula for a minute until this makes sense. Stare at this equation, stare at this blob right here for a minute until it makes sense. And then it's like one of those, oh, that's interesting kind of cool moments. Yeah, that's interesting. The first and fourth terms in the final expansion are 0, and determinant of AD minus AD plus BC, which is AD minus BC, right. Right, okay. Carrying this out for n by n matrices leads to the complete expansion of the determinant. Right, this is using the linearity. Right, this is using the row linearity of the determinant. Okay. Leads to a complete expansion of the determinant. The formula, determinant of A is equal to the sum over all permutations P of the sine of P times, what does that mean again? A1 P1 to AN PN, in which the sum is over all permutations of the n indices, and sine of P is the sine of the permutation. Okay. For a 2x2 matrix, the complete expansion gives us back formula 1.4.2. For a 3x3 matrix, the complete expansion has 6 terms because there are 6 permutations of the indices, right? So they're generally n factorial permutations. Yeah, so this determinant thing is interesting, but in practice, n factorial grows too bigly to be a useful formula. Okay. Right, it's this weird stitching pattern. Okay. And as an aid for remembering this expansion, one can display the block matrix A bar A. The three terms with positive signs are the products of the terms along with the three diagonals that go downward from left to right, and the three terms with negative signs are the products of the terms on the diagonals that go downward from right to left. Of course, will not work with 4x4 determinants. Wonderful. The complete expansion is more of a theoretical than practical importance. Right, this is what I just said. Unless n is smaller, the matrix is very special. It has too many terms to be useful for computation. Its theoretical importance comes from the fact that determinants are exhibited as polynomials in the n-squared variable matrix entries aij with coefficients plus and minus 1. For example, if each matrix entry aij is a differentiable function of a variable t, then because sums and products of differentiable functions are differentiable, determinant A is also a differentiable function of t, right? The cofactor matrix of an n by n matrix A is the n by n matrix cof A, whose ij entry is cof A ij is minus 1 to the I plus j determinant AJI. Alright. Whereas before, AJI is obtained by crossing out the jth row and ith column. So the cofactor matrix is the transpose of the matrix made up of the n minus 1 by n minus 1 minors. Right, I noticed the ij and then becomes ji. If you need to compute a cofactor matrix, it is safest to make the computations in 3 steps. First, compute the matrix whose ijth entry is the minor determinant aij, then adjust signs, then finally transpose. Here is the computation for a particular a is equal to that, okay. Then 4 minus 1, so a is equal to 1, 1, 2, 0, 2, 1, 1, 0, 2. I assume this is the determinant aij matrix. 4 minus 1 minus 2, 2, 0 minus 1, minus 3, 1, 2. 4, 1 minus 2, minus 2, 0, 1, minus 3, 1, 2. Okay, so this is determinants, adjust the signs, take the transpose. Yeah, that's, one is this matrix is, I don't have the pointer with, I do, but I don't feel like plugging it in right now. If I need to write something, I'll plug it in. Theorem 1.6.9. Let A be an n by n matrix and let C equals cofactor A be its cofactor matrix, and let alpha equals determinant of A. If alpha is not 0, then A is invertible, and A inverse is equal to alpha inverse times C. That's interesting. In any case, CA is equal to AC is equal to alpha times the identity matrix. Here, alpha I is the diagonal matrix with diagonal entries equal to alpha. For the inverse of a 2 by 2 matrix, this theorem gives us back formula 1.1.17. The determinant of the 3 by 3 matrix A, whose cofactor matrix is computed in 1.6.8, above happens to be 1, so for that matrix, alpha inverse is equal to cofactor A. How much longer? Okay, we're almost done. We show that the ij entry of the product CA is equal to alpha if I is equal to j and is 0 otherwise. Let AI denote the ith column of A. Denoting the entries of C and A by Cij and Aij, the ij entry of the product CA is sum over nu of Ci nu, A nu j. Which is equal to minus 1 to the v plus I AVI, AVJ. Okay. So this is just the this is the definition of the product. Okay, I need the drawing pad. Need the drawing pad. Where's the drawing? Where's the cable? So uh-oh. For some reason the drawing pad is not working. Anyway. So the first, this is the definition of a matrix multiplication, and this is just substituting the definition of C I knew in, I think. When I is equal to j, this is the formula for the determinant of expansion by minors on column j. So the diagonals are equal to alpha. Okay, I'm not going to go check that, but that argument would make sense. Suppose that I is not equal to j. We form a new matrix M in the following way. You know, this book is hard to read because you have to keep jumping around, and then just the notation is not good, but I don't think that's really Arden's fault. But the proofs are very. You can understand the explanations, but the proofs are very too much jumping around, too much. You can't just kind of read it straight through, and I guess that's something I'm going to work on in my revelations, is make sure that you can read it without jumping around. I guess in a textbook it's kind of, well, also it's I mean, we see how dense it is, and the textbook is 600 pages, 500 pages, something like that. So it's dense, and it's 500 pages of dense. Anyway, so when I is equal to j, this is the formula for determinant by expansion by minors on column j. So the diagonal entries of CA are equal to alpha as claimed. Suppose that I is not equal to j. We form a new matrix M in the following way. The entries of M are equal to the entries of A, except for those in column I. The ith column Mi of M is equal to the jth column Aj of A. Thus the ith and the jth columns of M are both equal to Aj, and determinant of M is equal to 0. I read that out loud, and I absorbed none of it. Okay. Forming a new matrix M, the entries of M are equal to the entries of A, except for those in column I. What? We form a, except for those in column I. The ith column Mi of M is equal to the jth column column Aj of A. Thus the ith and jth columns of M are both equal to A, and determinant, or both equal to Aj, and determinant of M is equal to 0. Okay. Let D be the cofactor matrix of M with entries Dij. The II entry of Dm is... Okay, that first is definition of matrix definition. This is our definition of matrix multiplication. And I guess this is just substitution. I guess this is our formula for determinant. I'm not going to go check that, but that sum is equal to determinant of M, which is 0. On the other hand, since the ith column of M is crossed out when forming M nu I, that minor is equal to A nu I. And since the ith column of M, I can't follow this. Okay, let me zoom out, and maybe it'll be easier for me to follow the larger structure. Okay. Let me read it quietly and try to figure out what's going on, and then once if I figure out what's going on, I'll try to explain. You know, most of what I read for years, most of what I read was math textbooks. And I was, Craig and I did a podcast back in April. The clips are up on the Craig Cannon Clips channel, which is linked down below, where we were reading Chapter 1 of Munker's Topology. And there's something I noticed in there, which is Craig was reading it very linearly, and I don't read linearly. I like jump. I think it's jump around. I read something and then go back 2 paragraphs. It's very, my reading has a lot of jumps in it, and Craig's was very linear. I don't know which is better, but I'm now wondering that if I got my habit of jumping around and kind of skim, jump, go deeper, kind of very, very kind of chaotic. If you tracked my eye movement, I got to start like recording my face. If you tracked my eye movement, I don't think it would be, if I'm just reading naturally, it wouldn't be linear. It wouldn't be go right, left to right, straight down. It's very jump around. And I mean, if I was if I was reading this as a paper book, I would have the book, and then be flipping back and forth. So when he says 1.6.1, and that's actually helpful when you're reading it the first time through, because then you start. Readin does this really well. Readin is the best math author of all time, and I think I'm going to start. There's too many books I want to read on this channel, but Readin is so good that he's going to make the cut, I think, even though he does glow in the dark. Readin is the best math author I've ever read, without any doubt. There's not a close second. He is the best. There really is just nobody who even compares to Readin. I lost my train of thought. Let me go back to reading. Oh yeah, well, Readin is good at. For some reason, you have this experience a lot when you're reading Readin, which you get hung up on a sentence, like you're reading it, and you start reading a sentence and you go, wait, what the fuck? What the hell is he talking about here? And you spend like 3 days getting hung up on this sentence, and you can't figure out what the hell that sentence is. Like, what do you do? And then you're, driving somewhere 3 days later, and suddenly it hits you. You finally get that sentence, and suddenly a bunch of shit that you kind of understood, or maybe understood the wrong way, suddenly all of a sudden makes sense all at once. And Readin is incredible in the sense that he is both the best author for pedagogical, for learning materials, and also his books are the best reference materials. I've never met a book, I'm sure there are books, that are both the best introductory material and the best reference material. The Bible, I guess, is the best introductory and best reference material for Christianity, but that's sort of a special case because, in some sense, Christianity is the Bible. It's right. I'm not going to go into what Christianity is, but Readin is just incredible at that. Anyway, that's not what we're reading about. We're reading about Artin, who is Readin, anyway, we're gonna have to read Readin. I also, yeah, let's get back to Artin. All right, Artin. Trying to read this and figure out what the hell's going on. Okay. So the larger structure of the argument is he's forming some random quantity, showing that it's equal to 0, and then showing that that random quantity is equal to the thing we want. Okay, I'm not going to be able to figure out how this works, I think, at a level deeper than that. Oh, let me just read it straight through, and I don't know. Suppose that not I is not equal to j, so I'm starting... Oh, I can see my cursor if it's over here. Here we go. I'm starting right here. Suppose that I is not equal to j. We form a new matrix M in the following way. The entries of M are equal to the entries of A except for those in column I. The ith column Mi of M. You know, usually when I'm reading math, as soon as I start to see an argument, my brain fills in the rest of the argument, and then I can understand it, and then I just have to read and make sure I didn't get any details wrong, which I usually don't do. I just kind of assume the rest of the argument. But so usually what it is I start to see an argument and I go, oh, I recognize exactly the argument that's going on here, just I can see the pattern. And here I have absolutely no idea what the hell this argument is. And so I can understand he's showing that he's constructing a quantity, showing that it's equal to 0, and showing that that's... And where the hell did D come from? Where is D? D is the cofactor matrix of M. The II entry of dm is that, okay. Okay, I understand that. That sum is equal to the determinant of M, which is 0. I. The ith column of M is equal to the jth column of A. Okay, so he's like copying a column. And then multiplying that new matrix by the cofactor matrix and showing that that is equal to the determinant of M, which is 0. So since the ith column of M is crossed out when forming M nu I, that minor is equal to A nu I. Since the ith column of M is equal to the jth column of A, M nu I is equal to A nu J, so the II entry of dm the ith column of M is crossed out. Okay, I understand that. Right, because, okay, so then otherwise M is equal to A, and so if you cross out that column, then if you cross out the column from both of them in particular, then the resulting matrices will be equal. The ith MVI is equal to AVJ. Okay, right, that because the ith column of M is equal. Okay, that makes sense. So the II entry of dm is equal to sum over nu of minus 1 to the nu plus I, A nu I, V A nu J. Okay. Where dm Okay, so he's just doing substitution because... Why is the drawing pad not working? That's annoying. My mouse works, but the drawing pad, does it... If I open up the Paint program, does it also not? No, the Paint program works, so it's just the... Anyway, his argument here is basically for all the... Okay, I'm just gonna... And these are matrices. That's Erlang type syntax, sorry. And these are rationals or reals, I guess. Is also equal, so these, so these two formulas represent the same quantity. That's the point he's making. Which is the ij entry of CA is 0, which is the ij entry of C. Okay, I kind of understand. And this is the same formula as this. And we proved that this is 0. This is 0. Therefore, this is 0. Therefore, if I is not equal to j, this is 0. Okay. That argument is too detailed for me to really follow it on first pass, but I gotta... Okay, maybe we'll come back to this. Alright. Okay. Computation of the product AC is done in a similar way. Oh my god. At some point, this... Okay. This is what I mean by proofs for the sake of proofs. There is so much detail in this argument that it is impossible for a midwit like me to follow it. And I'm sure if I was, if I had the big CIA Jew brain, then I could follow it. But I don't. I can't follow this. Anyway. I can kind of figure out it's like, I can hear every note but can't hear the melody. What is it? There was an analogy used to describe like the emotions of psychopaths. It's something like they can hear every note but don't hear the music. And that's basically what it is where I'm reading this. I can understand a lot of the steps, but I don't see the music. I don't see how everything sort of fits together. And by the time I figured out how the proof works, I forgot what we're even trying to prove. So, yeah, that's the thing I got to work on in my revelations, is making sure that when I write, it's very linear and you don't have to jump back and forth like this. Anyway, there's sort of this fetishization in math of writing something very minimally, and I don't have that fetishization. I think as long as I think clarity is the most important thing, right? This fake rigor and minimalism, that's not my thing. I go for clarity, and then everything else is less important. Clarity and computability and a lot of examples. That's my approach. Well, maybe not a lot of examples, but I try to use a concrete. For me, I only need 1 or 2 examples before I get the idea, but I think most people will need 20 examples. And realistically, I probably should have more than 20 examples. It's just after 1 or 2, I kind of like, okay, I get the idea. Let's move on. Anyway, that's all I wanted to say. Or what I was doing a lot was same example, and so I'd pick a very small, simple problem, and then every time I encountered a new concept, how does that new concept apply to this problem? And so you kind of get an incredible amount of depth looking at a single problem rather than sort of shallow dives into a lot of different problems. I don't know which is better, probably a mixture of both. This is, anyway, what's this, a general algebraical determinant, this is a quote at the end, a general algebraical determinant in its developed form may be likened to a mixture of liquids seemingly homogeneous, but which, being of differing boiling points, admit of being separated by the process of fractional distillation. James Joseph Sylvester. All right. Wow. Okay, these problems. I'm not going to solve problems from a textbook on. Definitely, I'm assuming that you went and bought the textbook. That's why I've been linking it in the description. Go buy the textbook. And I'm not. Maybe I shouldn't even show the exercises. Go do a lot of the exercises. The reason I'm doing these videos, I'm not trying to like. I have worried about like is this. I think there might technically be some copyright issue. First of all, my thought about that is like 90% of YouTube is reactions, and this is way closer to fair use. If reactions count as fair use, this is way closer to. This is the determining factors are like, is it educational? Am I doing commentary? I am doing way more commentary, and this is way more educational than reaction videos. So I know reaction videos sometimes have copyright issues, and I'm also not really making any money. I'm not going to. I think on Rumble the videos are monetized automatically. I don't know how to turn that off. But I'm not making any money off of this. I'm mostly just doing this for myself, and then on the off chance it might help somebody. But I'm doing way more commentary and it's way more educational than the lowbrow, than reactions to rap videos or something like that. Anyway, that's all I have to say. Thank you for watching. This is end of art in chapter 1. Next chapter, I guess, is groups. I think I want to read. I want to do Apollonius's treatise on conics, maybe Euclid's Elements as well. Apollonius's treatise on conics, and then I don't know. I think for a while. So the next chapter is group theory. This discrete Dirichlet problem looks really interesting, and I'm not going to give the answers to, because somebody might give these as homework problems, and I actually, why am I playing nice with the university system? I hate the university system. Yeah, CIA, Bourbaki. It was the CIA got a group of CIA agents together that pretended to be a single mathematician named Nicholas Bourbaki. He was like the Nicholas Bourbaki was what was that guy's name? Nicholas Bourbaki was the Pierre Delecto of mathematics. Anyway, and of course he spoke in French. That's the CIA's favorite language. And it's the best way to disguise that you're part of the CIA is to speak French. Nobody suspects the French of being CIA agents except me, because I'm the smartest mathematician who ever lived. Anyway, That's all I have to say. Thank you. I've concluded the video like 5 times. Thank you. Bye.